Today, we'll talk about machine learning. We'll focus on what it is and why you'd want to use it. Machine learning teaches computers to do what comes naturally to humans: learn from experience. It's great for complex problems involving a large amount of data with lots of variables, but no existing formula or equation that describes the system. Some common scenarios where machine learning applies include when a system is too complex for handwritten rules, like in face and speech recognition, when the rules of a task are constantly changing, as in fraud detection, and when the nature of the data itself keeps changing, like in automated trading, energy demand forecasting, and predicting shopping trends. Machine learning uses two types of techniques: unsupervised learning, which finds hidden patterns in input data, and supervised learning, which trains a model on known input and output data so that it can predict future outputs. Unsupervised learning draws inferences from data sets that don't have labeled responses associated with the input data. Clustering is the most common unsupervised learning technique. It puts data into different groups based on shared characteristics in the data. Clustering is used to find hidden groupings in applications such as gene sequence analysis, market research, and object recognition, among many others. On the other hand, supervised learning requires each example of the input data to come with a correctly labeled output. It uses this labeled data, along with classification and regression techniques, to develop predictive models. Classification techniques predict discrete responses, like whether an email is genuine or spam. Essentially, these models classify input data into a predetermined set of categories. Regression techniques predict continuous responses, like what temperature a thermostat should be set at, or fluctuations in electricity demand. Again, the big difference here between supervised learning and unsupervised learning is that supervised learning requires correctly labeled examples to train the machine learning model, and then uses that model to label new data. Keep in mind, the techniques you use and the algorithms you select depend on the size and type of data you're working with, the insights you want to get from the data, and how those insights will be used. We'll talk more about these techniques in the next few videos. For now, that was a very brief overview of machine learning. Be sure to check out the description for more information.
Unsupervised machine learning looks for patterns in datasets that don't have labeled responses. You'd use this technique when you want to explore your data, but don't yet have a specific goal, or you're not sure what information the data contains. It's also a good way to reduce the dimension of your data. As we've previously discussed, most unsupervised learning techniques are a form of cluster analysis, which separates data into groups based on shared characteristics. Clustering algorithms fall into two broad groups: hard clustering, where each data point belongs to only one cluster, and soft clustering, where each data point can belong to more than one cluster. For context, here's a hard clustering example. Say you're an engineer building cell phone towers. You need to decide where and how many towers to construct. To make sure you're providing the best signal reception, you need to locate the towers within clusters of people. To start, you need an initial guess at the number of clusters. To do this, compare scenarios with 3 towers and 4 towers to see how well each is able to provide service. Because a phone can only talk to one tower at a time, this is a hard clustering problem. For this, you could use k-means clustering because the k-means algorithm treats each observation in the data as an object having a location in space. It finds cluster centers, or means, that reduce the total distance from data points to their cluster centers. So that was hard clustering. Let's see how you might use a soft clustering algorithm in the real world. Pretend you're a biologist analyzing the genes involved in normal and abnormal cell division. You have data from 2 tissue samples, and you want to compare them to determine whether certain patterns of gene features correlate to cancer. Because the same genes can be involved in several biological processes, no single gene is likely to belong to one cluster only. Apply a fuzzy c-means algorithm to the data, and then visualize the clusters to see which groups of genes behave in similar ways. You can then use this model to help see which features correlate with normal or abnormal cell division. This covers the 2 main techniques, hard and soft clustering, for exploring data with unlabeled responses. Remember, though, that you can also use unsupervised machine learning to reduce the number of features or the dimensionality of your data. You do this to make your data less complex, especially if you're working with data that has hundreds or thousands of variables. By reducing the complexity of your data, you're able to focus on the important features and gain better insights. Let's look at 3 common dimensionality reduction algorithms. Principal component analysis, or PCA, performs a linear transformation on the data so that most of the variance in your dataset is captured by the first few principal components. This could be useful for developing condition indicators for machine health monitoring. Factor analysis identifies underlying correlations between variables in your dataset. It provides a representation of unobserved latent or common factors. Factor analysis is sometimes used to explain stock price variation. Non-negative matrix factorization is used when model terms must represent non-negative quantities, such as physical quantities. If you need to compare a lot of text on web pages or documents, this would be a good method to start with, as text is either not present or occurs a positive number of times. In this video, we took a closer look at hard and soft clustering algorithms, and we also showed why you'd want to use unsupervised machine learning to reduce the number of features in your dataset. As for your next steps, unsupervised learning might be your end goal. If you're just looking to segment data, a clustering algorithm is an appropriate choice. On the other hand, you might want to use unsupervised learning as a dimensionality reduction step for supervised learning. In our next video, we'll take a closer look at supervised learning. For now, that wraps up this video. Don't forget to check out the description below for more resources and links.
A supervised learning algorithm takes in both a known set of input data and corresponding output data. It then trains a model to map inputs to outputs so it can predict the response to any new set of input data. As we've previously discussed, all supervised learning techniques take the form of either classification or regression. Classification techniques predict discrete responses. Use these techniques if the outputs you want to predict can be separated into different groups. Examples of classification problems include medical imaging, speech recognition, and credit scoring. Regression techniques, on the other hand, predict continuous responses. A good example of this is any application where the output you are predicting can take any value in a certain range, like stock prices and acoustic signal processing. Now, let's say you have a classification problem you're trying to solve. Let's take a brief look at just a few classification algorithms you could use. The logistic regression algorithm is one of the simplest. It is used with binary classification problems, meaning problems where there are only 2 possible outputs. It works best when the data can be well separated by a single linear boundary. You can also use it as a baseline for comparison against more complex classification methods. Bagged and boosted decision trees combine individual decision trees, which have less predictive power, into an ensemble of many trees, which has greater predictive power. It is best used when predictors are discrete or behave nonlinearly, and when you have more time to train a model. Keep in mind, there are many other classification algorithms. These are just 2 of the most common. There are plenty of algorithms to choose from if you have a regression problem as well. Linear regression is a statistical modeling technique. Use it when you need an algorithm that is easy to interpret and fast to fit, or as a baseline for evaluating other, more complex regression models. Nonlinear regression helps describe more complex relationships in data. Use it when data has strong nonlinear trends and cannot be easily transformed into a linear space. Again, these are just 2 common regression algorithms you can choose from. There are many more you might want to consider. Now, let's put it all together and see how this process might look in the real world. Say you're an engineer at a plastic production plant. The plant's 900 workers operate 24 hours a day, 365 days a year. To make sure you catch machine failures before they happen, you need to develop a health monitoring and predictive maintenance application that uses advanced machine learning algorithms to classify potential issues. After collecting, cleaning, and logging data from the machines in the plant, your team evaluates several classification techniques. For each technique, the team trains a classification model using the machine data, and then tests the model's ability to predict if a machine is about to have a problem. The tests show that an ensemble of bagged decision trees is the most accurate, so That's what your team moves forward with when developing the predictive maintenance application. In addition to trying different types of models, there are many ways to further increase your model's predictive power. Let's briefly talk about just 3 of these methods. The first is feature selection, where you identify the most relevant inputs from the data that provide the best predictive power. Remember, a model can only be as good as the features you use to train it. Second, feature transformation is a form of dimensionality reduction, which we discussed in the previous video. Here are the 3 most commonly used techniques. With feature transformation, you reduce the complexity of your data, which can make it much easier to represent and analyze. Hyperparameter tuning is a third way to increase your model's accuracy. It is an iterative process where your goal is to find the best possible settings for how to train the model. You retrain your model many times using different settings until you discover the combination of settings that results in the most accurate model. So that's a quick look at supervised learning. In our next video, we're going to take a deeper look at an example machine learning workflow. Until then, be sure to check out the description below for more machine learning resources. Thanks for watching.
With machine learning, there is rarely a straight line from start to finish. You'll find yourself trying different ideas and approaches. Today, we'll walk through a machine learning workflow step by step, and we'll focus on a few key decision points along the way. Every machine learning workflow begins with 3 questions. What kind of data are you working with? What insights do you want to get from it? And how and where will those insights be applied? The example in this video is based on a cell phone health monitoring app. The input consists of sensor data from the phone's accelerometer and gyroscope, and the responses are the activities performed, such as walking, standing, running, climbing stairs, or lying down. We want to use the sensor data to train a classification model to identify these activities. Now let's step through each part of the workflow to see how we can get our fitness app working. We'll start with data from the sensors in the phone. A flat file format such as text or CSV is easy to work with and makes importing data straightforward. Now we import all that data into MATLAB and plot each labeled set to get a feel for what's in the data. To pre-process the data, we look for missing data or outliers. In this case, we might also look at using signal processing techniques to remove the low-frequency gravitational effects. That would help the algorithm focus on the movement of the subject, not the orientation of the phone. Finally, we divide the data into 2 sets. We save part of the data for testing and use the rest to build the models. Feature engineering is one of the most important parts of machine learning. It turns raw data into information that a machine learning algorithm can use. For the activity tracker, we want to extract features that capture the frequency content of the accelerometer data. These features will help the algorithm distinguish between walking, which is low frequency, and running, which is high frequency. We create a new table that includes the selected features. The number of features that you could derive is limited only by your imagination. However, there are a lot of techniques commonly used for different types of data. Now it's time to build and train the model. It's a good idea to start with something simple like a basic decision tree. This will run fast and be easy to interpret. To see how well it performs, we look at the confusion matrix, a table that compares the classifications made by the model with the actual class labels. The confusion matrix shows that our model is having trouble distinguishing between dancing and running. Maybe a decision tree doesn't work well for this type of data. We'll try something else. Let's try a multi-class support vector machine, or SVM. With this method, we now get 99% accuracy, which is a big improvement. We achieved our goal by iterating on the model and trying different algorithms. However, it's rarely this simple. If our classifiers still couldn't reliably differentiate between dancing and running, we'd look into other ways to improve the model. Improving a model can take 2 different directions. Make the model simpler to avoid overfitting, or adding complexity in order to improve accuracy. A good model only includes the features with the most predictive power, so to simplify the model, we should first try and reduce the number of features. Sometimes we look at ways to reduce the model itself. We can do this by pruning branches from a decision tree or removing learners from an ensemble. If our model still can't tell the difference between running and dancing, it may be due to overgeneralizing. So to fine-tune our model, we can add additional features. In our example, the gyroscope records the orientation of the cell phone during activity. This data might provide unique signatures for the different activities. For example, there might be a combination of acceleration and rotation that's unique to running. Now that we've adjusted our model, we can validate its performance against the test data we set aside in pre-processing. If the model can reliably classify the activities, we're ready to move it to the phone and start tracking. So that wraps up our machine learning example and our overview video series about machine learning. For more information, check out the links below. In our next series, we're going to look at some advanced topics related to machine learning, such as feature engineering and hyperparameter tuning.
Machine learning algorithms don't always work so well on raw data. Part of our jobs as engineers and scientists is to transform the raw data to make the behavior of the system more obvious to the machine learning algorithm. This is called feature engineering. Feature engineering starts with your best guess about what features might influence the thing you're trying to predict. After that, it's an iterative process where you create new features, add them to your model, and see if the result improved. Let's take a simple example where we want to predict whether a flight is going to be delayed or not. In the raw data, we have information such as the month of the flight, the destination, and the day of the week. If I fit a decision tree just to this data, I'll get an accuracy of 70%. What else could we calculate from this data that might help improve our predictions? Well, how about the number of flights per day? There are more flights on some days than others, which may mean they're more likely to be delayed. I already have this feature from my dataset in the app, so let's add it and retrain the model. You can see the model accuracy improved to 74%. Not bad for just adding a feature. Feature engineering is often referred to as a creative process, more of an art than a science. There's no correct way to do it, but if you have domain expertise and a solid understanding of the data, you'll be in a good position to perform feature engineering. As you'll see later, techniques used for feature engineering are things you may already be familiar with, but you might not have thought about them in this context before. Let's see another example that's a bit more interesting. Here, we're trying to predict whether a heart is behaving normally or abnormally by classifying the sounds it makes. The sounds come in the form of audio signals. Rather than training on the raw signals, we can engineer features and then use those values to train a model. Recently, deep learning approaches are becoming popular as they require less manual feature engineering. Instead, the features are learned as part of the training process. While this has often shown very promising results, deep learning models require more data, take longer to train, and the resulting model is typically less interpretable than if you were to manually engineer the features. The features we use to classify heart sounds come from the signal processing field. We calculated things such as skewness, kurtosis, and dominant frequencies. These calculations extract characteristics that make it easier for the model to distinguish between an abnormal heart sound and a normal one. So, what other features do people use? Many use traditional statistical techniques like mean, median, and mode, as well as basic things like counting the number of times something happens. Lots of data has a timestamp associated with it. There are a number of features you can extract from a timestamp that might improve model performance. What was the month, or day of week, or hour of the day? Was it a weekend or holiday? Such features play a big role in determining human behavior. For example, if you were trying to predict how much electricity people use. Another class of feature engineering has to do with text data. Counting the number of times certain words occur in a text is one technique, which is often combined with normalization techniques, like term frequency, inverse document frequency. Word2vec, in which words are converted to a high-dimensional vector representation, is another popular feature engineering technique for text. The last class of techniques I'll talk about has to do with images. Images contain lots of information, so you often need to extract the important parts. Traditional techniques calculate the histogram of colors or apply transforms such as the Haar wavelet. More recently, researchers have started using convolutional neural networks to extract features from images. Depending on the type of data you're working with, it may make sense to use a variety of the techniques we've discussed. Feature engineering is a trial and error process. The only way to know if a feature is any good is to add it to a model and check if it improves the results. To wrap up, that was a brief explanation of feature engineering. We have many more examples on our site, so check them out.
ROC curves are an important tool for assessing classification models. They're also a bit abstract, so let's start by reviewing some simpler ways to assess models. Let's use an example that has to do with the sounds a heart makes. Given 71 different features from an audio recording of a heart, we try to classify if the heart sounds normal or abnormal. One of the easiest metrics to understand is the accuracy of a model, or in other words, how often it is correct. The accuracy is useful because it's a single number, making comparisons easy. The classifier I'm looking at right now has an accuracy of 86.3%. What the accuracy doesn't tell you is how the model was right or wrong. For that, there's the confusion matrix, which shows things such as the true positive rate. In this case, it is 74%, meaning the classifier correctly predicted abnormal heart sounds 74% of the time. We also have the false positive rate of 9%. This is the rate at which the classifier predicted abnormal when the heart sound was actually normal. The confusion matrix gives results for a single model, but most machine learning models don't just classify things, they actually calculate probabilities. The confusion matrix for this model shows the result of classifying anything with a probability of greater than or equal to 0.5 as abnormal, and anything with a probability of less than 0.5 as normal. But that 0.5 doesn't have to be fixed, and in fact, we could threshold anywhere in the range of probabilities between 0 and 1. That's where ROC curves come in. The ROC curve plots the true positive rate versus the false positive rate for different values of this threshold. Let's look at this in more detail. Here's my model, and I'll run it on my test data to get the probability of an abnormal heart sound. Now let's start by thresholding these probabilities at 0.5. If I do that, I get a true positive rate of 74% and a false positive rate of 9%. But what if we wanted to be very conservative? So even if the probability of a heart sound being abnormal was just 10%, we would classify it as abnormal. If we do that, we get this point. What if we wanted to be really certain and only classify sounds with a 90% probability as being abnormal? Then we'd get this point, which has a much lower false positive rate, but also a lower true positive rate. Now, if we were to create a bunch of values for this threshold in between 0 and 1, say 1,000 trials evenly spaced, we would get lots of these ROC points, and that's where we get the ROC curve from. The ROC curve shows us the trade-off in the true positive rate and false positive rate for varying values of that threshold. There will always be a point on the ROC curve at 0, 0. In our case, everything is classified as normal. And there will always be a point at 1, 1, where everything is classified as abnormal. The area under the curve is a metric for how good our classifier is. A perfect classifier would have an AUC of 1. In this example, the AUC is 0.926. In MATLAB, you don't need to do all of this by hand like I've done here. You can get the ROC curve and the AUC from the perfcurve function. Now that we have that down, let's look at some interesting cases for an ROC curve. If a curve is all the way up and to the left, you have a classifier that for some threshold perfectly labeled every point in the test data, and your AUC is 1. You either have a really good classifier, or you may want to be concerned that you don't have enough data or that your classifier is overfit. If a curve is a straight line from the bottom left to the top right, you have a classifier that does no better than a random guess. Its AUC is 0.5. You may want to try some other types of models, or go back to your training data to see if you can engineer some better features. If a curve looks kind of jagged, that is sometimes due to the behavior of different types of classifiers. For example, a decision tree only has a finite number of decision nodes, and each of those nodes has a specific probability. The jaggedness comes from when the threshold value we talked about earlier crosses the probability at one of the nodes. Jaggedness also commonly comes from gaps in the test data. As you can see from these examples, ROC curves can be a simple yet nuanced tool for assessing classifier performance. If you want to learn more about machine learning model assessment, check out the links in the description below.
Machine learning is all about fitting models to data. The models consist of parameters, and we find the value for those through the fitting process. This process typically involves some type of iterative algorithm that minimizes the model error. That algorithm has parameters that control how it works, and those are what we call hyperparameters. In deep learning, we also call the parameters that determine the layer characteristics hyperparameters. Today, we'll be talking about techniques for both. So, why do we care about hyperparameters? Well, it turns out that most machine learning problems are non-convex. This means that depending on the values we select for the hyperparameters, we might get a completely different model. By changing the values of the hyperparameters, we can find different and hopefully better models. Okay, so we know we have hyperparameters, and we know we want to tweak them. But how do we do that? Some hyperparameters are continuous, some are binary, and others might take on any number of discrete values. This makes for a tough optimization problem. It is almost always impossible to run an exhaustive search of the hyperparameter space since it takes too long. So traditionally, engineers and researchers have used techniques for hyperparameter optimization, like grid search and random search. In this example, I'm using a grid search method to vary two hyperparameters, box constraint and kernel scale, for an SVM model. As you can see, the error of the resulting model is different for different values of the hyperparameters. After 100 trials, the search has found 12.8 and 2.6 to be the most promising values for the hyperparameters. Recently, random search has become more popular than grid search. How could that be, you might be asking? Wouldn't grid search do a better job of evenly exploring the hyperparameter space? Let's imagine you have two hyperparameters, A and B. Your model is very sensitive to A, but not sensitive to B. If we did a 3x3 grid search, we would only ever evaluate 3 different values of A. But if we did a random search, we would probably get 9 different values of A, even though some of them may be close together. As a result, we have a much better chance of finding a good value for A. In machine learning, we often have many hyperparameters. Some have a big influence over the results, and some don't. So random search is typically a better choice. Grid search and random search are nice because it's easy to understand what's going on. However, they still require many function evaluations. They also don't take advantage of the fact that as we evaluate more and more combinations of hyperparameters, we learn how those values affect our results. For that reason, you can use techniques that create a surrogate model, or an approximation of the error as a function of the hyperparameters. Bayesian optimization is one such technique. Here, we can see an example of a Bayesian optimization algorithm running, where each dot represents a different combination of hyperparameters. We can also see the algorithm's surrogate model, shown here as the surface, which it is using to pick the next set of hyperparameters. One other really cool thing about Bayesian optimization is that it doesn't just look at how accurate a model is. It can also take into account how long it takes to train. There could be sets of hyperparameters that cause the training time to increase by factors of 100 or more, and that might not be so great if we're trying to hit a deadline. You can configure Bayesian optimization in a number of ways, including expected improvement per second, which penalizes hyperparameter values that are expected to take a very long time to train. Now, the main reason to do hyperparameter optimization is to improve the model. And although there are other things we could do to improve it, I like to think of hyperparameter optimization as being a low effort, high compute type of approach. This is in contrast to something like feature engineering, where you have higher effort to create the new features, but you need less computational time. It's not always obvious which activity is going to have the biggest impact, but the nice thing about hyperparameter optimization is it lends itself well to overnight runs, so you can sleep while your computer works. That was a quick explanation of hyperparameter optimization. For more information, check out the links in the description.
The phrase machine learning brings to mind complex algorithms that use lots of computations to train a model. But computations on embedded devices are limited in the amount of memory and compute available. Now, when I say embedded devices, I'm referring to objects with a special purpose computing system, so think of things like a household appliance or sensors in an autonomous vehicle. Today, we'll discuss the different factors to keep in mind when preparing your machine learning model for an embedded device. Different types of models require different amounts of memory and time in order to make a prediction. For example, single decision trees are fast and require a small amount of memory. Nearest neighbor methods are slower and require more memory, so you might not want to use them for embedded applications. Another thing to keep in mind when determining which models to use on an embedded device is how you will get your model to the device. Most embedded systems are programmed in low-level languages such as C, but machine learning is typically done in high-level interpreted languages such as MATLAB, Python, or R. If you have to maintain code bases in two different languages, it is going to be very painful to keep them in sync. MATLAB provides tools that automatically convert a machine learning model to C code, so you don't need to manually implement the model in C separately. So what if, after converting a model to C, you find out that it isn't going to meet the requirements of your system? Maybe the memory footprint is too big, or the model takes too long to make predictions. You could try other types of models and see if the code meets the requirements. Maybe start with a simple model such as a decision tree. Alternatively, you could go back earlier in the process and see if you can reduce the number of features in the model. You can use tools such as neighborhood component analysis, which are useful for determining the impact that the features have on the results. If you see that some features are weighted low, you could drop them from your model, making the model more concise. Certain types of models have different reduction techniques associated with them. For decision trees, you can use pruning techniques, where you drop nodes that provide the smallest accuracy improvement. Depending on your use case, any of these tactics may be appropriate. Hardware considerations, network connections, and budget are all key factors that will influence design decisions. This was just a quick overview of embedding machine learning models. For more information on preparing models for embedded devices, see the links below.